All right, here's a What the Physics video. This one is on magnetism still. Specifically, we're going to be talking about the right-hand rule and maybe some applications about it. So, to remind ourselves what the right-hand rule is, everyone needs the right hand. Hopefully, you didn't forget. But there's the open palm right-hand rule, which has to do with an external magnetic field. And then there's the curled right-hand rule. So we'll do the curled one first. And if you recall, let me go ahead and pull that up. Looks something like this. Okay, so I use a pencil to represent the wire. I put the pointy end as the direction of the current flow. Put that pencil in my hand. So right now I'm holding a pencil that is pointing up, so that means the current is pointing up. I wrap my right hand around the pencil, the easy way, not the hard way. Don't break any fingers. The thumb is now pointing in which direction? Upwards, just like the current is. So your thumb is representing the direction of the current. The fingers are representing the direction of the magnetic field. So in this case, it is wrapping around on kind of the, I guess, going around the y-axis. If I were to look down upon it, as in I'm looking straight at the pointy end of my pencil, I guess, let's see, I would see this as going counterclockwise. Yes? Making sense? So that's the direction of the magnetic field. It all depends on what location I'm looking at it from, though. If I were saying, oh, what if I were looking at it from the bottom end of my pencil? Whoop. Okay. Or what if I were looking at it from the side, there? Is it going in? Is it going left? Is it going right? You do have to be careful. Okay? If we are talking about, say, the magnetic field right here, it would be coming out of the board. Coming out of the board. And how would I represent that again? What little markings would I use? The dots. Okay, the dot is the one when it's coming toward you, right? On this side, it's going into the board, so that would be an X. Yeah. In front of the wire here, it would be going to the. It would be going to the. Wrapping our hand around. Which way would my fingers be pointing? Which way are my fingers pointing? They're pointing to the right. I have my pencil here. My fingertips are pointing to the right here, yes? Okay. If I were to focus on the area behind where the wire is, it would be pointing to the left. Yes, indeed. Okay, so that's the curled right-hand rule. We can also speak in terms of wrapping it around a solenoid. Okay, you can either pretend that you're grabbing hold of one of the wires here. Let's say you grab this wire right here. Which way is the current going in that particular one, in that particular line? Current is going downwards, as we see by that little arrow. So which way should my thumb be pointing? It should be pointing downwards. If I grasp hold of this wire, now my thumb pointing downwards, which way are my fingers going to be pointing? Inside of this little coily area. It would be, so grab hold of this wire. Okay, my pencil is now pointing downwards to represent, my thumb is pointing downwards. I'm grasping it, and which way are my fingers pointing here? As if they were inside of this coiled area. Listen, which way are they pointing? To the, make sure you know your left from your right. I believe that's to our right, yes? Okay, bless you. Okay, so they're pointing to the right. The other version of this right-hand rule that you can use is, it's a modified version of the curled right-hand rule, which is shown here. You just put your fingers in the direction of the current flow, and then your thumb is the magnetic field for the inside of the solenoid. Some teachers don't like to discuss that one because most folks like to say, hey, always use your thumb as your current and your fingers as your magnetic field. But what else? Figured I'd just show you. And then there's, when you have an external magnetic field, you use the open palm right-hand rule. When the thumb is, as before, the direction of the current, the fingers are the direction of the magnetic field, and your palm is the direction of the force. Okay, so if we can look at some of these example problems that I'd asked you to work on. Okay, so draw and label the direction of I through a wire coming out of the page. Let's make this a tad larger. Okay, so if I want to draw a wire coming out of the page, what symbol do I use to show that? The dot. Yes, indeed. Okay, so that means something is coming out of the page. I know it's the wire. Okay, I can label this current. Okay, and I'm going to switch colors just to demonstrate I'm talking about the magnetic field now. Okay. Draw the direction a compass would point when it is held above the wire. Okay, so you've already drawn a little dot on your page, and you can get your pencil and have the pencil pointing up out of the page, yes? And you grasp hold of it with your right hand, and it's going in what direction? Okay, it's going around in a circle. If I were to look down upon this circle, it would be doing what way? Okay, it would be going counterclockwise. Okay, going counterclockwise. Just one second. Now, if it says draw the direction a compass would point when it is held above the wire, which way would that be? This is the area above the wire, so that is going to be what? To the left. Yes. We got to get Beyonce out here to sing to the left. To the left. Okay. Okay, so number 2. How do I draw this? The wire is going into the page, so what do? I draw an X. Okay, and that is the current. I guess I can label this magnetic field. Okay, and what do I do here? Get out my right hand and I point my thumb in what direction? Into the page, or in your case, like downward into the table, and whatever, okay? In my case, it's into the board. Make sure that you're being careful on your whole directional thing, okay? There's 6 directions you can give. Left and right, hopefully that's pretty straightforward. Up and down, be careful, that's up the page and down the page, and then there's into the page and out of the page, okay? So up does not mean out of the page, okay? So let's see. So my fingers are wrapping around this way. So beep, 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 beep. Okay, and so here it's going to the right. Okay, yes, I have to incorporate that. Okay, I was spoken to the other day saying like, Fair, your last PowerPoint didn't include any jokes. I'm like, oh. And I thought through it. I'm like, oh, you're right. I'm sorry. I don't know what else to do with. So
It didn't have any potential.
it didn't have any potential. I figured you'd just be attracted to it out of the material itself. I didn't realize it was my charge to do all these jokes in here as well. And I finally just looked at them. I'm like, why are you asking me for this? I should stop fielding questions right now, yes? People are now vomiting, so that's let's go on, okay? So, this guy, okay. This is a solenoid. We have the current coming out there. It's coming out of the positive end. This can be tricky because not only do we have to look at the direction that the current is flowing, we've got to look at the direction the wire is wrapped. So, let's see, it comes around behind and then the wire goes this way. So the current is going downwards there, yes? And in fact, it would be a good idea for you to draw in the currents for each of those little guys there. Okay, just so you can help visualize what's going on. Okay, now if we were to grab onto one of those wires, which way would our thumbs point? It would, well, our thumbs would point, okay, when I'm saying one of these wires, I mean one of the coiled wires. Okay? Because we're only paying attention to the solenoid section, right? So the thumb would point downwards, so our fingers inside of the coiled area would point which way? To the right. To the right. Oh, yeah, I'm just going to keep doing that. Okay, that's inside. And in actuality, as we said before, they're always supposed to loop around. Okay? Now, we could also do it the second version of the curled right-hand rule. Which way, if I were to do it the alternate version of the curled right-hand rule, which way would my fingers be going? They're wrapping around in the direction of the current. So I'd be like grasping hold of this and I don't know how I can, it's like my palm would come in from behind the solenoid and my fingers would be pointing downwards in the front, yes? Okay, and my thumb would be to the right. Okay, number 4, similar situation. You say, oh, but there, look at this. The current is this away, right? So I bet the magnetic field is the other way, right? Not so simple, right? Okay, look at that. The current is still pointing downwards on the front side. So whether I use the original flavor of the curled right-hand rule or I do the alternate version of the curled right-hand rule, magnetic field is pointing which way? Okay, yes, it's pointing to the wrong. Okay. Okay, so hopefully that makes sense. Moving on. RHR or RHR, right-hand rule. Example 2. Number 1, find the direction of the force on a proton moving through the magnetic fields as shown. So remember, this isn't just for wires with current in them. This is for charges as well. Because after all, they're kind of the same thing, yeah? Just talking about a specific particle instead of a stream of particles. So, part A, which way is the field going? Into the field. The magnetic field is into the board or into your page, yes? So that's, my fingers are doing what? Pointing inwards, right? Okay. Now notice, this is an external magnetic field. So which right-hand rule am I using here? Open palm. So I point my fingers into the page or into the board or whatever you're referencing. And then, what is this V referring to? Velocity of the positive charged particle. So that's my thumb. So it's going to be pointing upwards, up the page. Okay, so which way is my palm going right now? To the left. Okay, so I'll use green. So I'm going to draw a little particle here and draw that in as the force. Yes. Okay, with that in mind, do the next. Okay? So my fingers are pointing which way? To the right, and my thumb is pointing which way? Upwards. So my force is going which way? Okay, it's into the page. I can write, in case you're not comfortable with all the symbols, you can say force is into the page, but how should I draw that? As an X. No, dot is coming out. So X is going inwards. Okay? The force is going inwards. And I can label that as F. Okay, C. Fingers, which are the magnetic fields, they're going which way? Downwards. My thumb is the direction of the charged particle, going which way? Leftwards, so that means the force is outward. So I'm going to draw a dot. Usually we draw the dots with a little circle around them. You can draw circles around the X's, but I don't know. Some publishers do, some don't. Okay, and then how about this? Okay. I see. Yes, you're trying to walk like an Egyptian over there. Okay. If I reference that song, does anyone even know?
Yes.
Walk like. Okay. And then, well, I'm acting it out now. Not that. It's probably best for the people watching this from home are the true winners because they can't see me trying to dance. Right. Yes, all three of them. So the dots are pointing which way? Okay, and the dots are representing what? The fingers, which are the magnetic field. So my fingers are coming out of the board. The thumb is pointing to the left, so my force is okay. Hopefully, you're recognizing that, and that's up the page, remember, right? Not up out of the paper, it's up the page. Hopefully, you're recognizing you should be able to narrow this down immediately to, if nothing else, a 50-50 shot. Because in order for this to work properly, magnetic field has to be on one axis, the velocity has to be on another axis, perpendicular, and the force has to be on a third axis. And they all have to be perpendicular to each other. So the field is on the X, velocity is on the Y, the force is going to be on the Z. Now, is that positive Z or negative Z? I don't know. That's what our right hands are for. Okay? They say, Farrah, I recognize what you just said, but wait a minute. Dun, dun, dun! That's it's a little cray-cray. Okay? I said in order for us to get our maximum strength, they need to be perpendicular to each other. So they technically have to be perpendicular to each other. Not for maximum strength. Okay? As long as they're not parallel, we'll get something out of it. So the magnetic field here is on the positive X. It's going to the right. So that's my fingers. The V, I don't care about the X piece of the V. I care about the which piece? The Y piece. Okay? So that's my thumb pointing upwards, my fingers pointing to the right. Which way is my palm going? Into the board, which I draw with an X. Good. Star. What? No. Okay. And same thing here. B is apparently on the X-axis, so the V is on which axis? On the Y, or at least the part I care about is on the Y-axis. Okay, so that means, which way is the force going? Out of the page. Should I draw that how? Dot. Little circle. Make it happy. Okay. Now that was all part A, or part 1, or number 1, I guess. Number 2, repeat, assuming the moving particle is an electron. Is that going to matter? Heck yeah, it will. Positive charge versus negative charge, that will mean a difference. What do I do here? Well, yeah, you could technically use your left hand, okay? This isn't the hokey pokey. It's like, oh, put your right hand in. Oh, no, no, put your left hand in. Okay? The way I had suggested you do it is do it with your right hand and then just say it's opposite day and flip the direction. Okay? If you do it with your left hand, okay. Some teachers get really huffy about, don't ever use your left hand. Roar. And then they breathe fire. And it's impressive. But I don't quite understand why they're so against it. But seeing as we just went through all of these, what can we say about, say, like part A? It's going to go to the right. So I'll draw that in blue.
17 degrees above.
What? 17. Okay. And B? Well, so this one, for the negative, okay, so I'm going to demonstrate for an electron, negative charge is in blue. You'll have to, unless you have different colors, which maybe you can do, you'll have to distinguish a little better. Okay, so this one is going to be coming out of the page. Okay. C is going to be going which way? It's going into the page. D, and hopefully this is making sense as we go through, right? I can still use my right hand. My fingers are pointing outwards, out of the page. My thumb is pointing to the left. The force on a positive would be going upward, but it's opposite day, so that means it's going which way? Downwards, yes indeed. Okay, and then this one would be in, and then this one, I don't want to draw it on that X, I'll just draw it over there. Okay, right. And then, draw and label the direction of the magnetic field above and below a wire carrying current toward the right. So, which rule do I use? Curled or open? This is curled. Okay, so, because, how do you know this? How do you know it's good? Well, it's a wire, but that's not enough. Okay, you can have a wire going through an external magnetic field. Example number 2. Okay, the important part is, well, whether or not there's an external magnetic field. Okay, if there is no external magnetic field, there's nothing for the created magnetic field to really interact with. So, yeah. Thumb is to the right. If I'm talking about, let's see, red I think would be the correct one here. So above, it's going to be coming which way? The magnetic field will be coming which way? Above the wire. I'm by above the wire, we're talking about this area right here, above the wire. Wrap my fingers around here. Which way are my fingertips pointing? Out of the page. So I draw that with the dot and a circle, right. Okay, and then, okay. All right. Number 2, I already kind of gave it away, that has its own external magnetic field. So we're looking for the force. So I think that was green. So let's see. Open palm. Thumb is pointing to the right. Fingertips, these X's are the magnetic field. So which way are they pointing? Say again? No, which way are my fingers pointing? Into the page. So my force is, right, my force is up the page. Right. Okay, and then finally, number 3, Hopefully you can visualize what it's about to show us anyhow. But let's grab hold of, well, not grab hold, let's look at the charge right here, and it's a positive, so I'll use the green. So right now we're looking at this guy right here. Okay, so it's a positive, and the magnetic field is which way? Into the board, and the charge is going which way? To the left. So that means the force is going downwards, down the page. Okay. Let's skip the next one. Let's go to like the 9 o'clock position, which is right over here. Okay. Magnetic field is still in the same direction, but the velocity is which way?
Yeah.
Is down the page. So that means the force is going to be
Right.
to the right. Say, whoa, it's changing on me. Heck yeah, it is. Okay. Let's look at the 6 o'clock position. Okay, the field is still into the board. The direction of the velocity is to the right, so the force is upwards. Right. Okay. Hopefully you're able to see all these other ones. Okay. All these are the forces. So what's it going to do? It's going to make a pretty circle. Indeed. Okay. Cool. Okay, so hopefully we were able to recognize that whole concept linked to circular motion. That's one of the reasons I really like doing magnetism, because it just brings everything back together. And it's kind of like when we were doing conservation of energy, and we were able to relate all this stuff like circular motion. And it's just one of those fun topics that just works as a big culmination. Okay, so when we're talking about a charged particle going around through a magnetic field, if certain circumstance, or if certain situations, settings, whatever you want to call them, are correct, then we can see nice little loopies going on. Okay, so let's see, the right-hand rule will tell us which way it's going to curve. Remember that we're using the right-hand rule for positive charge. It can just as easily be a negative charge going through, though, and you'd either swap to the left hand, which some teachers might growl at you about, or you can just pretend that it's opposite day. Okay? If we are having these go around in circles, that means we get to use circular motion centripetal force equation. So we've got this guy going on right here. And so here's my centripetal force equation. M times V squared over R is equal to the magnetic force, which I showed you earlier in the slides, QVB. We're just going to assume that they're all right angles to each other, so we'll drop off the whole sine theta biz. Notice that one of the velocities will cancel out. So this guy here and then this square here. So I'm left with this. M times V divided by R is equal to QB. Now, I'm not going to solve it in any more detail because it depends on what we're going to solve for. I can solve for the mass of the particle, or I can solve for the magnetic field through which it's traveling, or I can solve for where it's going to hit, or all sorts of different things. Okay, this is a really great application in terms of what's called a mass spectrometer. Has anyone ever heard of that before? Okay, where have you heard about it?
It's usually just been like in the news, like they I think created it, just like interesting.
Okay, so you might have heard about it on the news. Some, I guess, a lot of like crime scene type things will reference mass spectrometers. Like someone mentioned, oh, they said about it on Bones and CSI and stuff like that. Right. So what this does is it helps us figure out what these particles are. So it sends one of these particles through this field, and this is actually a combination of a magnetic field and an electric field. So these parallel plates are affecting the electric, or are giving an electric field. Then this magnetic field here is also there. Now, I don't really know much detail in terms of how a mass spec actually works. I just know about it in terms of physics theory, the real basics. So, do they use this setup? Do they have this magnetic field at a different strength of this magnetic field? I don't know. Maybe they can just turn this off and guide the charged particle in because of the parallel plates focusing only on the electric field. Or maybe they have the magnetic field on as well as the electric field, and the electric field is designed to compensate or cancel out for the magnetic field. So that's how the charge is able to go in a straight line. I don't actually know. Okay, but the point is, they're able to guide it through this little opening. By it, we mean some type of particle. And as it comes out here, so you can see it's going to take this little path. You say, well, Fair, how do you know it takes this little path? Do you actually see the particles? No. These particles are invisible. And by that, I mean quite literally not able to be seen. They're so small. However, we can look to see where the tracks of these were. Or in other words, let's say you've got an invisible baseball. I'm not going to go into how you have an invisible baseball. Let's just say you have a baseball that you cannot see. Okay? And in front of you, there's a whole bunch of windows. Don't actually do this. What do you think I'm going to say? Okay? Take the baseball and throw it at the windows, and you'll see which one breaks. You actually see the baseball? No. But you see the path that the baseball took, right? That's effectively what this is. It's got a whole bunch of sensors, like imagine a whole bunch of windows for these particles to crash into. You don't actually see the particles, but the sensor will pick up, oh, something just smashed in. Okay? And we can say, oh, well, the radius of this circle goes from here to there, and then there to there, so it's twice the radius. So I can figure out very quickly what the R value is. If I know what the magnetic field is, I know what the Q is from this earlier part, if you're able to balance the particle so it goes through without going up or going downwards. You're able to figure out what the mass is. Okay, so that's pretty cool. That's a really great application. So you can see with the magnetic field and the electric field, they both affect charges. But remember, magnetic fields only affect moving charges. And while both fields can redirect a charge, they redirect them differently. An electric field is only going to work in one direction. Up, down, left, right, in, out, whatever. But the force is always going to be along that same axis. So if a positively charged particle is coming in through here, what are these field lines in orange telling us? What are these field lines telling us, folks? What is the direction of the electric field in this picture? This is the electric field that we're talking about. Okay, so these orange guys right here, the orange guys are telling us the direction of the electric field, and they would be pointing downwards, right? So that would imply that up here is a positive charge, down here is a negative charge. Remember, the electric field lines are going away from a positive and toward a negative, right? Okay, it's the path a positively charged particle would take, yes? Okay. So if this guy is a positive charge and there's no magnetic field going on in the background, what would happen? Well, it'd be just like gravity, right? It would cause it to go downwards, just like in projectile motion. Okay, so what shape would that give us? It is a curve, but be more specific. It's a parabolic curve or parabola, yes. Okay, that is different from once it enters into this magnetic field. because the force's direction is always changing. What shape is this? Circular shape. Okay, so we can actually tell what type of field it is, if by nothing else, looking at what shape the curve is. Okay, and if we looked on, let's get this guy out of the way. If we looked on the Cabrillo website, question number 5 actually talked about this whole, what is the shape from an electric field, or what is the shape of the path of the charged particle going through an electric field. Okay, so hopefully you kind of realize that. And we already said parabolic, and then the magnetic field will do the circular motion. And the force and, let's see, what did I say here? Force and the velocity are always perpendicular to each other. Okay, cool. Okay, I'd like you to do this example problem. Okay, this has to do with charge, so it's more like a discovery type thing. So we're incorporating what we've already used. We can say, okay, is this going to be a positively charged particle, or negative, or neutral, or how does this one compare to that? Maybe the masses are different. Okay, so try these out. These I thought were kind of fun. Okay, so this is definitely something that they can use in real life accelerators when we're trying to figure out what the particle is. Okay, so like the Large Hadron Collider, for example. I'm not going to say they have no idea what particles are going to come out, but there are a number of different particles that can come out, and it's important that they're able to test as many characteristics as possible. So some of the particles might be affected by a magnetic field and some not. Okay, so this would help us figure out what type of particles they were. So this guy here is curling around like this, curling in a, what direction would we say this? Well, not up, down, left. I mean, clockwise or counterclockwise? Yeah? Which one? Counterclockwise, yes. Okay, good. Now, these charges are going through an external magnetic field, and so what is the direction of that external magnetic field? Into the board, right, and that is going to be my fingertips pointing into the board, yes? Okay, and we said for circle going around like this, the force is going to be inwards, yes? Okay, so that means the charged particle, and it's going this way right here, and then when it's up here, I'm sorry, it's going this way to the right, it should be more specific, when the force is going upwards. Over here, the force is going to the left, and the velocity is going to the right. So that sounds like it matches up with the standard right-hand rule, which means that the particle is positive. Yes, indeed. Okay. This one, what is its curve like? There is no curve, which implies what? It is neutral. There's no charge. And then finally, this one here, it is curving. Is it curving like the other one, though? No. Okay. We recognize that the velocity at this spot right here is going upwards. The force is going to be going to the right. So I can do this with my fingers, right? My thumb would be pointing upwards. The force is to the right, but that would imply that my fingers are pointing out of the board. In other words, the magnetic field is pointing out of the board. Is that what the case is, though? No. So this must be opposite day. That means it's a negative charge. Okay? So let's see. Like I said, well, I'll just mark it again. Okay? This is positive. This is neutral. And this guy is negative. Right. Okay, and here, let's scoot that out of the way. We have a hydrogen nucleus and a helium nucleus, they're launched at the same speed and in the same field. How should their radii compare and why? Well, what was our equation from earlier? Yes?
Mass times velocity divided by radius is equal to charge and the effect of the magnetic field.
Okay. What are we likely to be solving for here? We're asked about the radii, so I should rearrange this solving for r, yes? Okay, so I'm going to do a little switcheroo. I'm going to multiply r on both sides and divide by qb, yes? So mv divided by qb equals r, yes? And I was asked for a ratio, because I don't actually have specific numbers to plug in. That's perfectly fine. We're going to do a ratio. So I'm going to do, let's see, I'll actually move these over. Stay there. Okay. I'm going to do a ratio of R for helium divided by R for hydrogen. Okay. So I'm going to just rewrite all these, this guy over here. So this is the mass for helium, velocity for the helium, divided by the charge for the helium, and the magnetic field for the helium, all of which is divided by mass for the hydrogen, velocity for the hydrogen, charge for the hydrogen, and magnetic field for the hydrogen. Okay? So far, so good, yes? Indeed. What did I get told earlier that is the same? Velocity and the who? Velocity and the field are the same. So I can cancel out this guy, and then the fields, the B's, yes? Okay. Well, that's cool. It looks a lot simpler now. But first of all, it's still one of those ugly, complex, compound, whatever fractions. Okay? So that's a little scary. But I suppose I could try to reorganize things a little bit, but it's not actually that bad, because what do I know about helium versus hydrogen in terms of mass and charge? How does helium compare to hydrogen? Okay, hydrogen is the first element, helium is the second element, right? Okay, so it's the first element, it's got what charge? Positive charge, because it said it's just the nucleus, right? So it's a +1. Okay, so let me write these kind of off to the side. So Q hydrogen is equal to +1. Q helium is equal to what? +2. Okay, and you're like, +2 what? Well, it doesn't matter. Q if you want, because they're going to cancel out. It's a ratio. Okay? How do their masses compare? Are they the same mass? What's hydrogen made of? Just a single proton, right? So the mass of hydrogen is just 1. Okay, 1 proton, but fine. Okay, what's the mass of helium? It's got 2 protons. It's also got what? 2. What else is in the proton or in the nucleus, folks? Neutrons. It's got 2 neutrons. So the mass is actually 4, because protons and neutrons are effectively the same mass. There's a slight difference, but we don't really care for this purpose. Okay? So this is actually pretty cool, because now I can just do some ratio biz over here. I'll rewrite the equation MHE over QHE, all of which is divided by mass of the hydrogen, charge of the hydrogen. And I can just plug in those guys. Let's switch over to my reds. Okay. So the mass of the helium was what? 4 units, whatever they are. They're going to cancel out. Okay. The charge of the helium was what? Says it on the board. Could someone speak, please? It's the charge of helium is 2. Okay. 2Q if you'd like, right? It's going to cancel. Divided out by the mass of the hydrogen, which is 1, divided by the charge of the hydrogen, which is 1. Okay. Can we handle this? What do we get? 4 over 2. Well, okay, I'm sorry, I did forget this charge. Those cancel, and whatever the units are for here, unit, those cancel. So I'm left with what? 2. So the ratio of the helium circle should be twice that of the hydrogen circle. Ta-da. You say, well, I don't know. Is that actually the case? If I were to measure this distance, that's for the, which one? Which particle is that? That would be for the hydrogen, right? And I compare it to, let's, green. That, I guess, right there. Somewhere out there is the radius. Okay. Yeah. The green is twice the size as the black. Okay. Cool.